In this presentation, we're going to discuss the properties of light. If you had a charged object and that charged object was vibrating, then it's going to create an electromagnetic wave. And this electromagnetic wave is made up of a vibrating electrical field and also a vibrating magnetic field and these two fields are traveling perpendicular to each other. These electromagnetic waves are actually capable of transmitting energy through a vacuum. If you remember about our mechanical waves that we studied when we talked about sound, that has to have a medium to transport its energy, unlike our electromagnetic waves that don't need a medium. So, how fast are these waves traveling? As these electromagnetic waves travel through free space, they're always going to be moving at the same speed. And this is because as they are moving through space, as the electrical wave changes, it induces a changing magnetic field. And then as this magnetic field changes, it induces a changing electrical field. So they propagate each other. And they have to keep moving at the same speed because if it was to slow down, then the changing electrical field would generate a weaker magnetic field, which would generate a weaker electrical field, and the wave would die out. Or if the electrical field got stronger and generated a stronger magnetic field, then it would keep getting stronger each time. And we know this doesn't happen. The electrical fields and the magnetic fields stay at the same strength forever, as far as we know. And this fits in with what we know about the conservation of energy. We can't either destroy or create this energy, so the electromagnetic wave is going to continue traveling through a vacuum at the same speed. And the speed that it travels, these electromagnetic waves travel at, is what we commonly call the speed of light. And we can write that with just a c. The speed of light is about 300,000 kilometers per second. Okay? And again, this is the only speed at which those mutual electrical fields and magnetic fields can induce each other without losing or gaining energy. And when we talk about light, we're simply talking about those electric magnetic vibrations that are in a range that our eyes can detect. And the electromagnetic vibrations outside of that range still exist. We just can't see them. So if we look at the electromagnetic spectrum, we can see how we can classify these electromagnetic waves according to their frequency, how many times per second they vibrate. And if we look on the left, where we see like our radio waves, we can see that these are waves that have a relatively low frequency, maybe 1 million hertz. But if you look at the size of the wave is really long. It has a long wavelength. And when we look at some radio waves are actually from crest to crest bigger than a football field. So these waves can be quite large. As we start moving to the right, the waves get shorter, they get a shorter wavelength, but their frequency increases greatly. So when we get up to like microwaves, which are the waves we use to cook our food in microwave ovens, we can see we're getting over 1 billion hertz. If we shorten the wavelength and increase the frequency of our waves even more, now past 1 trillion hertz, now we start to get in what we call the infrared spectrum. And that infrared is right under the spectrum of light that we can see. So if we speed up our infrared waves a little bit more, shorten their wavelength, increase their frequency a little bit more, then we can see the spectrum of visible light. And as we look at the whole spectrum of electromagnetic energy, the visible light spectrum that we can see is very small. So a lot of this energy we can't really detect with our eyes or any of our other senses. Once we start going a little, we com- make those waves a little shorter still and their frequency get a little higher, then we go past the visible spectrum that we can see and we get into ultraviolet. And as the frequency gets even higher, then we start to get very small wavelengths like X rays and gamma rays. And again, our lower frequency waves have long wavelengths and they have a lower energy than our higher frequency waves. Those high frequency waves have short wavelengths and have more energy. So looking at all these different wavelengths from, millionths of a meter all the way up to football field size, do these wavelengths move at different speeds? And no, all the waves in electromagnetic spectrum, no matter what their frequency or their wavelength, move at the same constant speed, that speed of light, which we can write as c. In some ways, light is very similar to sound. Both are created by something that's vibrating. Remember, when we talked about sound, we talked about an object that's vibrating, such as our tuning fork there, sets up vibrations in a media such as air that we can hear as sound. And light is created similarly, but on a subatomic level. Light is actually created by the vibrations of electrons and atoms. And as we have all these vibrating materials, different materials respond to different frequencies of vibrations. So if we look at the electrons in glass, for instance, they vibrate in the same frequency that that say ultraviolet light sits on in the electromagnetic spectrum. So if ultraviolet light hits glass, that energy causes the atoms to vibrate, and because it vibrates in the same frequency, it resonates with the ultraviolet light and creates a very strong amplitude, just like the resonance we talked about with sound. These strongly vibrating atoms collide with each other, and as these atoms move and collide, they transform the energy from the ultraviolet light to heat. So when glass is exposed to ultraviolet light, it gets warmer. Our visible light, the light that we can see, has a lower frequency. And when this visible light hits glass, like window glass, it also causes the atoms to vibrate, but at a much lower frequency than ultraviolet light. So some of it is transformed into heat by the motion of the atoms, but a lot of the energy in visible light is transmitted by electrons through the glass. And this happens similar to this diagram we have here. So over here on the left, we have light coming in, exciting an atom, and that energy is absorbed by that atom. And then that atom passes the energy on to the middle atom. And then the middle atom passes that energy on to the atom on the right. And then the right atom releases that energy out of the glass and into the air on the other side. So what we can see here is as light, this energy, goes through the glass, we can actually say that this is not the same light that came here. This light here transferred its energy into the atoms of the glass, and then the atoms of the glass used that energy to create light on the other side. Infrared radiation also causes atoms to vibrate, but not fast, but only fast enough to create some heat, but not fast enough to transmit the light through the glass. It doesn't have enough energy to make the light go through the glass. So we can see here when we have some glass and we have light, say from the sun, that contains all these wavelengths coming to our glass, the ultraviolet is moving fast enough to cause the glass to resonate. And so the energy is transformed into heat. And then here in the infrared, again, now there's not enough energy to cause the atoms to emit light, but there is enough energy to heat the glass again. But in our visible wavelength, now the wavelengths are at a frequency that don't cause the glass to resonate, but it is a strong enough energy to cause the atoms of the glass to release light on the other side of the glass. And again, light through a vacuum, as we said before, is about 300,000 kilometers per second. and you can see that we write that value as C. And you can keep from getting confused with the C we use for, say, the small calorie, because this C is italicized instead of straight up and down. In Earth's atmosphere, the speed of light is slightly less than C, but from our purposes in this class, we're going to go ahead and round it off to C. If light is going through water, we can see that the speed is not quite C, but it's about 75% of C. Through glass, it's about 67% of C, and this depends on what type of glass we're looking at. It can be some glass allows light to come through faster, some glass slows it down more. And then diamonds slow light down to about 0.41 C, or 41% of the speed of light in a vacuum. So what happens to the frequency of light that gets transmitted through glass or any other transparent object? Well, the frequency of the light is going to remain the same. So when the light hits those atoms and excites those atoms to release light on the other side of the glass, it's the same frequency if it comes through clear glass. So the light we see on one side of the glass is the same frequency that we would see on the other side of the glass. What about the speed of light? What happens to the speed of light when it comes out of a glass or water? Well, we saw in the previous slide that the light is going to slow down as it goes through water or through glass, but once it comes out of the water, the glass, and it's back into a vacuum or our atmosphere, it's going to return to its original speed of C. So our atmosphere is transparent to all visible light. And it also lets some ultraviolet light waves through, but not a whole lot. Ultraviolet light can be very damaging to living tissue, especially UVA um, rays that have a lot of energy. These can cause sunburns and other damage to our tissues. UVB comes through our atmosphere pretty readily, and this is the UV radiation that can stimulate our skin to produce melanin, and so can cause a tan. And then UVC is a much less powerful UV ray that is almost completely blocked by our atmosphere. Most of the objects we see around us are opaque. And that means that they don't transmit light through them. Most of them absorb light without re-emitting it. So people are opaque. We can't see through people. We can't see through books. We can't see through furniture. All these things are opaque. And what happens when light hits these opaque objects is the atoms vibrate due to the energy from the light, and that's turned into random kinetic energy, internal energy inside the object. And so when objects are exposed to light, they can become slightly warmer. Some objects, opaque objects, react a slightly different way to light. For instance, let's look at this shiny polished piece of metal here. When light hits this metal, it causes free electrons in the metal to vibrate, and then those vibrating electrons emit their own light as a reflection. And we'll talk a great deal more about reflections next week. When we talk about beams of light, we often call small beams of light rays. And think about when we stand in sunlight. Some of the light rays are stopped by our opaque bodies, while the other light rays continue in a straight line path, say, to the ground. So those places where we block those light rays, we cast a shadow. And this is just a region where the light rays don't reach. We can see shadows here in this example of this orange that's been exposed to some light, and he's casting a shadow. And you can see on the picture on the left, the shadow looks nice and sharp and crisp. And happens when we have a large, faraway light source, such as the sun, or a small light source that's really close. We'll see this sharp kind of shadow. If we have a large nearby source or a smaller source that's far away, then we'll start to see a more blurry shadow like we see on the right. We can also affect how the shadow looks by bringing the object closer to the surface it's casting a shadow on or further away. So, for instance, on the left, if we hold the orange close to the wall where that shadow is being cast, the shadow is going to be a sharp one. If we move the orange away from the wall, then we're going to get a blurrier shadow. On our shadows, the middle part of the shadow is usually the darkest part on the inside. And then there's usually a lighter edge around the shadow that's not quite as dark as the middle. That total shadow in the middle is called an umbra, and that partial shadow that we see on the edges of the shadow is called a penumbra. And a penumbra occurs when some of the light is blocked, but some of the other light rays can fill it in. So it can also occur where light from a very broad source is only partially blocked, and so the light is coming from around the sides of the object. And we can see this effect when we look at this shadow cast by this vase of flowers. So we have a large source that's fairly far away from our flowers in the first picture. And you can see as the vase is very close to the areas casting the shadow on, it's a nice crisp shadow. As we start to move the vase further away, now some of the light rays from the large source come from around the vase and they make the shadow a little less stark and crisp and a little bit fuzzier. We see a more of a penumbra. And then as we move the vase even further away, now more light rays can fill in behind the vase. And you can see the penumbra much more clearly here, that kind of fuzzy gray area around the dark middle umbra of the shadow. We can see these shadows in, say, solar eclipses. The sun is a large light source, and then as the moon comes in front of the earth in between us and the sun, we can see these rays come at an angle and be blocked by the moon. And because the sun is so large, there's only a very small area that we have an umbra or a total eclipse. And because the sun is so large, there's a lot of light that gets around the edges. And so we'll see a penumbra or a partial shadow, partial eclipse. When we have a lunar eclipse, what's happening there is the moon is passing completely behind the earth into its shadow. And because the moon is so much smaller than both the earth and the sun, it's quite easy for the moon to be completely eclipsed or be completely in the earth's shadow. And this is a little different than when we say have a new moon where we really can't see the moon. On a new moon, it's basically because the moon is over here and the lit up side of the moon is facing away from us towards the sun. Over here with a full moon, the lit up side of the moon is facing us. But when we have a lunar eclipse, the moon is actually in the shadow of the earth. So how do we actually perceive this electromagnetic radiation that we call light? Well, we perceive light with our eyes. As light enters our eye, we have a transparent covering in the front called the cornea. And our cornea is a curved, clear structure, and the cornea does about 70% of the bending of light to help us focus on objects we're looking at. So the cornea bends the light, refracts it, and then it passes through an opening in our iris, and the iris is the colored part of your eye. And depending on how much melanin you have in your iris, your eye might be brown, it might be black, it might be blue or green, or any shade in between those. The opening in the iris is called the pupil, and it appears black mainly because there's no light being reflected from the pupil to an observer's eye. As the light passes a pupil, it reaches the lens, and the lens is sometimes called the crystalline lens. And the lens is a structure that's made out of clear proteins, and our ciliary muscles that attach to the lens can adjust the lens so that it can fine tune the focusing of the light that comes in through the cornea. And then the light goes through the vitreous humor that's in the back of the eye, and the light is focused onto our retina. The retina is the nervous layer of the eye, and it covers about 2/3 of the back of your eye. And the retina contains our rod and cone cells that actually react to the electromagnetic radiation we call light. And then the nerve cells, the rods and cones react to that light, they fire, and then that information is gathered by our optic nerve, sent to our brain, and processed as vision, as what we're actually seeing. The rods are much better at picking up low level light in black and white and movement, and our cones are much better at seeing brighter light in color. And speaking of color, why do we see different colors? Well, if you remember when earlier in the presentation when I was talking about electromagnetic spectrum and how radiation on the spectrum can have different frequencies, and the color of our visible light depends on what frequency that light is. If it's a relatively low frequency, it's going to appear to us to be red. If it's a relatively high frequency, it's going to look blue or violet. And here is our visible region of the electromagnetic spectrum. And you can see here, uh, and when we're looking at light that is about zero point 0.7 micrometers, or uh, zero point 0.7 of a millionth of a meter, that we perceive that as red. Any wavelengths longer than that we cannot perceive, or the nerve cells in our eyes can't pick it up, and we would call that infrared, so we can't see that. As the light waves get short, the wavelengths get shorter and shorter, we start to see different colors. Here we're seeing yellow. As the light wave gets shorter again, we perceive green. Shorter again, we start to see blue. And then the shortest wavelengths we can perceive are violet. And then as the waves get even shorter, it moves into the ultraviolet end of the spectrum. And of course, we can't see that. So we can only see between right here, the red end, and the violet end. There are other animals that can see in the ultraviolet spectrum, such as a lot of insects can see in the ultraviolet spectrum, but we cannot. So the reason we see different objects as different colors is because as those objects are exposed to light, some of the frequencies of light they will reflect, and some of the frequencies of light they will absorb. And the frequency of light that the object reflects is the color we see. So if we're looking at a green leaf off of a tree, that leaf is absorbing all the other frequencies of light, but just reflecting green frequency back to us, and that's why we see that leaf as green. What if we have an object that reflects all frequencies of light? Well, if we expose an object to light and it reflects all those frequencies in the visible spectrum back to us, we see that object as white, such as a white piece of paper, or a white towel, or a white t-shirt. What could we say about an object that absorbs all frequency of visible light? Well, in this case, there's nothing being reflected back to our eyes. So if we have an object that absorbs all frequencies of visible light, we perceive that as black. So if somebody has a black jacket, that jacket is absorbing all the frequencies of visible light, and so we see the jacket is black. Tires on a car, they're absorbing all frequencies, so we see the tires as black. And an object can only reflect the frequency that's present in the illuminating light. Now, with sunlight, as sunlight comes to Earth, it contains all the frequencies in visible light. So, usually we have the best color perception in natural sunlight. But what if we are exposing an object to maybe light just in one frequency, maybe red light or a green light? What do we see then? Let's take the example of our ball here. Over here on the left, we've exposed the ball to a natural light, so such as sunlight, and that light contains all the frequencies, all the colors in our visible electromagnetic spectrum. And in this case, the ball has absorbed all those frequencies of visible light except for the red, and it's reflected the red back to us, so we perceive the ball as red. Well, now instead of natural light that contains all frequencies, let's put the ball under a light that only emits red uh, wavelengths in the red end of the spectrum, so a red light. And again, the ball reflects those red frequencies back at us, so we still see the ball as red. But now let's put our ball under a green light. And so the only frequencies, the only wavelengths we have here are those of green light. In this case, the ball absorbs the green frequency just like it did over here in the natural light. But over here in this case, there's no red light for that ball to reflect back to us. So we perceive the ball as black because there are no wavelengths of visible light coming back to our eye from the ball. And it's really interesting that um, if we look at the ocean, the deep ocean, once you get a few hundred feet down from the surface of the ocean, long wavelengths such as red are unable to penetrate. Um, some of the shorter wavelengths can still penetrate, but as you go deeper, pretty soon none can. But in that mid depth region where we just have the very short rays penetrating, um, some fish that need to hide from their predators are actually colored red. They're bright red when you catch them and pull them up to the surface. And that's because at those deep depths, no red light can come down that far. So other fish looking at that red fish in the deeps of the sea can't see the fish at all because he looks black. We can also look at these different frequencies of light to see how light can be selectively transmitted as well as reflected. And if we have a transparent object like stained glass in a church window, the color of that transparent object depends on what light does it transmit through it. So for instance, look at this example. We have someone looking through a pane of blue glass. And what's happening here is the glass only reacts to the blue frequency to transmit it through the glass. The other frequencies are absorbed by the glass, and so the glass gets warmer from those other frequencies. But on the blue frequency, it allows it to excite those atoms to release blue light on the other side. So we see this particular pane of glass as blue because it's the only frequency that is allowed to come through that glass. We can use these properties of different frequencies to mix colors. For instance, on the computer screen that you're viewing this presentation on right now, that computer screen and TVs and stage lights, if you've ever been to a stage production, use something called additive color mixing. And this is where we take different colored lights or different pixels, and as we mix them, we can create different colors. So in your computer or your TV, it has red pixels, it has blue ones, it has green ones, and then it has black ones. And with those four pixels, your TV or your computer monitor can pretty much draw or create any color that it needs to just by what proportion of red, blue, green, and black it uses. If we have red and green together, the light, mixing that light, we get a yellow color. If we mix the red and blue together, we get that nice magenta. If we mix the green and blue, we get this cyan type color. And then if we mix all three colors together, we get white because again, we are adding light to the mix here. And if we have all wavelengths of visible light here, we see it as white. We can also have subtractive color mixing, and this is where we're using opaque pigments, such as when we paint a picture or we use our printers to print out a picture. And it uses slightly different colors. As you might have known if you ever had to buy ink for your color printer. It uses yellow, cyan, and magenta. And again, just like the colors in our additive color mixing, we can combine those three colors to create any color we need to. If we combine the yellow and the cyan pigments, we get green. If we combine the magenta and the cyan pigments, we get blue. And if we combine the yellow and magenta pigments, we get red. And because it's subtractive, we're taking frequencies of electromagnetic waves out of the picture. If we combine all of them, now we have an absence of frequencies reflected back to our eye. So we see that it's black when we move it all together. And it's really interesting to see that the subtractive color mixing and the additive color mixing are kind of opposites of each other. So as you see here, if you mix yellow and magenta, you get red. But in our previous slide, if we mix red and blue, we get magenta. And the same thing here, if we mix magenta and cyan, we get blue. But here, if we mix blue and red, we get magenta. So they're kind of opposites of each other.